at every level.
So you can see the motivation. A 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment. It's the most abundant element in the Earth's crust after oxygen. And it happens to store 9 times more lithium than graphite, which is the typical anode material in lithium-ion batteries today.
In recent times, the quest for enhanced battery capacity remains insatiable, as the pursuit of superior battery technology continues unabated. Significant breakthroughs have emerged that could pave the way for the next phase in battery advancements. Elon Musk himself has divulged plans for improving capacity to an impressive 500 Wh/kg, enabling rapid charging within just 6 minutes and delivering a range exceeding 600 miles. Today's episode delves into this groundbreaking battery technology. But prior to our exploration, we kindly ask you to express your support by subscribing to the channel and activating notifications, ensuring you stay up to date with the latest developments in the realms of EVs and green technology. Now, let's delve into the heart of today's episode. Silicon anode batteries represent an evolution of the widely employed lithium-ion batteries. In their initial iterations, lithium-ion batteries employed lithium as the anode material, which was subsequently replaced by silicon ions in the subsequent generation of battery technology, typically paired with carbon or graphite. What about the cost of this new battery? The projected production cost of silicon anode batteries is expected to dip below $100 per kilowatt hour by 2025, while lithium batteries currently cost around $134 per kilowatt hour. This technology not only enhances battery performance but also has tangible cost benefits. For instance, consider the 2023 Tesla Model Y with a battery size of 75 kilowatt hours. If it were equipped with a silicon anode battery costing $7,500, it would result in a savings of $2,550 compared to the $10,050 cost of a lithium battery. The cost of a battery primarily hinges on its constituent materials. On the whole, the manufacturing expense of a silicon anode battery is lower than that of its predecessors. Recent material price reductions have precipitated a significant decline in battery costs, and this downward trajectory is expected to persist. In summary, the production cost of a silicon anode battery is comparatively economical when compared to other battery types. This cost is not only lower than that of graphite batteries but also on par with lithium-ion batteries. Furthermore, researchers have harnessed silicon nanowires, seamlessly integrating them onto commercial graphite. This innovative approach could slash manufacturing costs by over 30%. This bodes well for both battery companies and customers, as it translates to substantial savings within financial budgets. But why is the silicon battery widely regarded as having the highest capacity in the industry? In contrast to lithium, a silicon anode battery boasts the highest volumetric capacity, reaching 9,786 mAh per cubic centimeter, which is nearly 3 times higher than lithium's relatively lower volumetric capacity of 3,271 mAh per cubic centimeter. Moreover, silicon undergoes discharge at an average voltage of 0.4 V, striking a stable balance that avoids issues like plating while retaining a reasonable open circuit voltage. This is notably lower compared to lithium batteries, which generally maintain a rated voltage of 3.7 V. In addition, a silicon anode battery could provide a runtime of 120 hours, a remarkable improvement of 15 times when compared to an 8-hour duration for a lithium-ion battery. This enhanced capacity is especially advantageous for real-world applications. Methods such as silicon nanoparticles and silicon encapsulation offer viable pathways to boosting efficiency without encountering complications. Why could silicon anode batteries charge to such a high capacity? The most impressive improvement, the silicon anode battery, has an extremely fast charging capability.
We've demonstrated that we can charge to 80% in under 6 minutes.
Whereas for this level of the battery, the lithium-ion battery used in Tesla Model 3 takes 40 minutes with 220V charging, which will save 34 minutes of silicon anode battery. Furthermore, Tesla has identified that a minor alteration to the battery design has the potential to amplify vehicle range by a substantial 20%. This hypothetical enhancement is illustrated through examples such as the Tesla Model Y, which could see its range increase from 316 to 379 miles. Similarly, the Model 3 might escalate from 250 to 300 miles, the Model X from 351 to 421 miles, and the Model S from 402 to 482 miles. This remarkable advancement is primarily attributed to the distinctive structure of silicon nanowire anodes. The nanowire arrangement presents relatively linear and unobstructed pores, in contrast to graphite anodes. As a result, anodes and electrons can navigate a direct pathway, facilitating rapid diffusion and remarkably swift charging capabilities. Consequently, consumer electronics powered by silicon anode batteries could potentially achieve 30% longer usage per charge than with standard batteries. Next, let's explore the exceptional attributes related to the energy density of this battery. Significant breakthroughs have emerged that hold the potential to usher in the next phase of battery technology. The substitution of graphite with silicon could result in batteries boasting an energy density that's notably 20% to 40% higher.
Why silicon? Because it has 10 times the capacity for lithium compared to graphite.
Additionally, it's worth noting that silicon batteries attain the highest gravimetric capacity, amounting to 4,200 mAh per gram-1, which surpasses lithium's comparatively modest gravimetric capacity of 3,828 mAh per gram-1 by an impressive 372 mAh per gram-1. Furthermore, researchers have disclosed that silicon anode batteries possess a high energy content of 500 watt-hours per kilogram, which is also equivalent to 1,300 watt-hours per liter. This translates to a significantly extended travel distance, nearly twice that of lithium-ion batteries with energy densities ranging between 260 to 270 watt-hours per kilogram, and a tenfold increase when compared to lead-acid batteries, which have energy densities ranging from 50 to 100 watt-hours per kilogram. The progress in the field of silicon anode batteries has indeed been considerable. Moreover, the utilization of silicon anode batteries preserves 80% of their capacity even after undergoing 500 cycles of recharging and discharging. This characteristic contributes to faster charging and discharging rates, ultimately enhancing the overall energy density. However, it's important to acknowledge that unlike carbon, silicon does possess inherent properties, such as lattice structure expansion by up to 400%, which presents certain challenges and considerations in its implementation.
It actually takes just 1 atom of silicon to store 4 atoms of lithium. And by contrast with graphite, with carbon materials, it takes 6 carbon atoms to store 1 lithium atom. So it's 24x atomically advantaged compared to carbon.
This distinction is achieved by structuring silicon into porous nanowires arranged akin to a forest, with shorter wires interspersed. This design enables the silicon to accommodate expansion while resisting cracking, effectively prolonging the lifespan of the silicon anodes. This innovation underscores the competitive edge of silicon anode battery technology. Numerous advantages stem from the energy density of silicon anode batteries. So, how do researchers leverage technology to realize this advancement? To attain optimal performance in silicon anode batteries, researchers employ both an ionic liquid and a silicon anode. The silicon anode operates via silicon ions, while the counter-electrode involves a small disk of lithium metal foil. These components are compressed together under high pressure, reaching 120 megapascals. The resultant configuration is known as a two-electrode cell. The Pacific Northwest National Laboratory team has developed a scalable technique for fabricating micron-sized porous silicon. This process yields abundant quantities of porous silicon while maintaining a consistent temperature during the etching phase. Additionally, this method permits the recovery and reuse of the etching agent. The team has also devised a specialized, high-concentration electrolyte tailored specifically for silicon anodes. This formulation substantially reduces leakage current and extends battery cycle life. The program's ultimate objective is to develop a silicon anode battery pack system with a capacity of 235 mAh per gram-1. This equates to a calendar life of 15 years and 500 discharge cycles. In terms of the resource origins for operating this silicon battery, where do they stem from? Silicon is environmentally friendly and stands as the second most abundant element in the Earth's crust. It ranks as the planet's second most plentiful material, thus negating any concerns about scarcity. Moreover, transitioning from graphite mined and refined from the Earth carries environmental benefits.
China produces the world's largest supply of silicon, with an estimated 4.5 million metric tons in 2019. Behind them is Russia, which produces 600,000. The US only produced about half of that, at 320,000.
What are the safety advantages associated with silicon batteries? The exceptional attributes of silicon position it as a highly capable contender within the battery industry. Opting for silicon instead of graphite could yield safer alternatives. Silicon anode batteries boast a range of safety features. These encompass a positive temperature coefficient, PTC, device, which safeguards against surges in high current. Additionally, a circuit interrupter halts the electrical path upon detecting excessive charging voltage. A safety vent is in place to release gas during abrupt pressure surges within the cell. An external electronic protection circuit, situated outside the cells, activates a solid-state switch at 4.30 V to ensure overcharge protection. Furthermore, a fuse is designed to cut off current flow once the skin temperature reaches 90 degrees Celsius. Solid-state silicon batteries emerge as a promising substitute for conventional lithium-ion batteries. They possess the capability to store a greater number of ions compared to traditional graphite-based anodes. Unlike batteries reliant on graphite, silicon-based counterparts exhibit a heightened energy density. However, certain existing lithium-ion battery manufacturers incorporate a minor portion of silicon, constraining their performance. In contrast, GDI's approach employs 100% silicon, resulting in significantly improved performance and a reduced risk of lithium dendrite formation. With this covered, let's delve into the application of silicon anode batteries within Tesla electric cars. But Tesla definitely confirmed that.
I mean, we have silicon in the cars that you're all in right now, are involved highly engineered, expensive materials in the scheme of things. Now, they're still great and they enable some of the benefits of silicon, they just don't.
Initially, the inaugural production of Tesla's Model S vehicle included a minor 5% infusion of silicon into the graphite composition. Remarkably, many companies still linger within the 5 to 10% silicon range. However, in a surprising twist, Tesla has progressed to utilizing 10 to 15% silicon amalgamation in their anode batteries to amplify capacity and energy density. The reality is that all vehicles confront challenges posed by extreme temperatures, but electric vehicles, in particular, are sensitive to both intense heat and cold. For Tesla's electric cars, the battery's optimal performance range spans around 20 degrees Celsius, with the reaction becoming more pronounced as temperatures shift from 122.22 to 127.07 degrees Celsius. This underscores how silicon anode batteries excel at significantly higher temperatures, surpassing lithium batteries by a factor of 2.3. Notably, the safe operating temperature window for lithium batteries spans from roughly 55 degrees Celsius to 80 degrees Celsius. Beyond 80 degrees Celsius, the cell encounters damage, with temperatures exceeding 130 degrees Celsius risking cell components melting and potentially triggering fires. Such instances trigger severe side reactions, hastening capacity decay. The path to realizing this type of battery has involved both platforms and models, with each model within a given platform sharing the same inverter. This inverter employs 24 silicon carbide devices, each housing 2 silicon carbide die in a single device package. Collectively, these 48 silicon carbide devices function within a 400V system with an equivalent simplified 160 kVA. In recent years, Sila Nanotechnologies, founded in 2011 by a group of former Tesla battery engineers and a materials science professor from Georgia University, has taken center stage. Their focus lies in advancing silicon anode technology, initially developed at Georgia Tech. Over the past decade, they have concentrated on refining materials and pioneering next-generation silicon anode chemistry for lithium-ion batteries, known as nanocomposite silicon. Concluding today's episode, what does the future hold for the silicon anode battery industry?
So I think it's now ready for the industry to really take it to the next level in terms of scale up the production.
In the final quarter of 2022, startups managed to secure an impressive investment of nearly $500 million. The global market size for silicon anodes is anticipated to expand from $1.2 billion in 2021 to surpass $208 billion by the close of 2031. This suggests that the industry is poised to advance to the next level, focusing on scaling up production. The innovation significantly elevates the energy density and capacity of the battery, not just incrementally, but through substantial leaps and bounds. The graphite anode, a creation that garnered the Nobel Prize and was introduced in 1991, currently powers electric vehicles. Yet, this technology marks the first viable contender capable of entirely replacing graphite anodes, and it stands ready for commercial deployment. Furthermore, the Biden and Harris administration are invigorating U.S. battery manufacturing by launching the American Battery Materials Initiative. This initiative aims to reinforce critical mineral supply chains and inject a significant investment of $2.8 billion into bolstering domestic manufacturing. Another promising avenue in lithium-ion battery development involves anodes constructed entirely of active silicon. Beyond Enovix, Amprius is also engaged in pursuing this approach. Amprius is actively developing electric vehicle batteries featuring low-cost silicon nanowire anodes and has secured federal funding for their project. To keep pace with this trend, a multitude of companies, including Sila, Enovix, Enovate, and Angstrom Materials, are diligently working towards the realization of high-performance silicon anode batteries. In summation, the silicon anode battery marks the commencement of a new chapter within the battery industry, attracting the attention of numerous major players who are entering the arena. Do you believe that silicon anode batteries hold the position of the best option among various battery technologies? Additionally, will silicon anode technology ultimately transition into mass production and be integrated into various devices throughout our lives? Your perspectives are welcome in the comments section below. If you found this content engaging, kindly show your support by leaving a like, subscribing if you haven't already, and don't forget to activate the notification bell to receive updates on new Techstar content. Once again, we extend our gratitude for tuning in, and we look forward to welcoming you back next time. Until then, stay safe and take care.